Hello everybody, welcome to this video looking at some more applications of Taylor polynomials. So in this video, the question we're going to address is how can we use Taylor polynomials to approximate the value of a function? So let's get started. So let's suppose we have some function f of x, which is equal to its Taylor series at a. So f is the sum of fn of a over n factorial x minus a to the n. Then one way to approximate the value of f of x is to just, instead of doing the infinite sum, which is actually equal to f of x, we could just do the finite sum. So kind of like we did with numbers, but now we're doing the same thing with functions. So let's compute this so-called nth degree Taylor polynomial. It's just the same thing, except we only add up to the nth term. And since we're adding up to the nth term, we don't want to use any n as our index anymore. We replace that by I. So it's the sum from I equals 0 to n fi of a over I factorial x minus a to the I. Just the up to the ith term in the Taylor series. So if we're approximating something, this is going to be our approximation, but we typically want to know how good is our approximation. So to know how good our approximation is, which is important, we want to be able to estimate this remainder, which is the difference between the true value f of x and the approximation, which is this nth degree Taylor polynomial Tn of x, which goes up to the nth term. And there are going to be two strategies to estimate the remainder, which are kind of based on things we've already seen. So if the Taylor series is alternating, then for every value of x, so we want to make sure that it's alternating for every x, whatever x is, then we can use the alternating series estimation theorem. So remember, we just said that if the series is alternating, then the error is at most the next term along. So that's what we're doing here, except here is the next term in the Taylor series. It's fn of plus 1 of a, x minus a to the n plus 1 over n plus 1 factorial. And if it's not alternating, then we have to use kind of a more reliable method, but it's a little bit harder to apply. We can use Taylor's inequality if the n plus first derivative is bounded by some constant m on an interval, where m is some bound we have to come up with. Then we get a remainder, an estimate for the remainder on the same interval. It's m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. So let's see some examples in both cases. So first example is going to be to approximate the cube root of x by a Taylor polynomial of degree 2 at center a equals 8. So calculating the Taylor polynomial is pretty much, it's just calculating the first few terms of the Taylor series. So that's going to be simple. But the hard part is how accurate is the approximation for x between 7 and 9. So finding the terms of the Taylor polynomial, that's, as I said, that's just finding the terms of the Taylor series up to the squared term, because we're going up to degree 2. So we'd have to compute f of 2, we have to compute f prime of 2 and f double prime of 2 just by differentiating and plugging in. So I skipped through that and I came up with the Taylor polynomial here. So 2 plus 1 over 12 x minus 8 minus 1 over 288 x minus 8 squared. And this is not necessarily alternating. For instance, if x is bigger than 8, then we would have 2 plus 1 over 12 x minus 8. These first two terms will be positive. So we'd have positive, positive. It's not going to be alternating. So we want to use the Taylor inequality. So Taylor's inequality said we had to come up with a bound on the derivatives. So here we're going to use Taylor's inequality because we're trying to bound the R2, the remainder, if we only go up to 2. That means we need to bound the third derivative. So we're using Taylor's inequality with n equals 2, center a equals 8. We need to bound for the third derivative. Okay, what is the bound for the third derivative? We compute f prime f, the third derivative at x is going to be 10 over 27 times 1 over x to the 8 over 3. Just using the fact that f of x is x to the 1 over third, we differentiate 3 times. This is what we get to. And we need to bound this between 7 and 9. So if 10 over 27 is not doing anything, it's just a constant multiple. We need to bound 1 over x to the positive power of 8 over 3 for x between 7 and 9. And as we said with fractions, if we want to bound it above, that means we need to find a number that's bigger. So we need to make it bigger. We can either make the top of a fraction bigger or make the bottom smaller. So here the x is on the bottom, so we want to make the bottom smaller. We replace the x by 7. So not by 9, but by 7, because it's on the bottom. And you can plug in, this is around 0.0021. And this is valid if x is between 7 and 9, or absolute value x minus 8 less than or equal to 1. So this is going to be our m. And now we can go ahead and plug that in Taylor's inequality. Taylor's inequality tells us that R2, the remainder if we only go up to the squared term, is bounded by the m we just found, so that's 0.0021, divided by 3 factorial, absolute value x minus 8 cubed. So here the absolute value of x minus 8 is less than 1, because the largest possible distance from 8 is 1, because we're going from 7 to 9. And we're dividing by 3 factorial, so we get, here is our bound, we plug it in, it's around 0.0004. Okay, so the steps with Taylor's inequality are to figure out what value of n we're using Taylor's inequality for. Here we're going up to the squared term, so that means we need to estimate R2. So Taylor's inequality tells us it's bounded by m over 3 factorial, absolute value x minus 8 cubed. come up with the bound on the derivative. That tells us what m should be, plug everything in into Taylor's inequality, and we get the estimate for the remainder. Okay, let's see an example in the opposite direction using the alternating series remainder estimate. So what is the greatest possible error in approximating sine x by x minus x cubed over 3 factorial plus x to the 5 over 5 factorial for x between negative 0.3 and 0.3? So this is the same thing as absolute value of x is less than or equal to 0.3. So the series for sine x is always alternating, right? It starts with x minus x cubed over 5 factorial plus x to the 5 over 5 factorial. There's going to be minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial, and so on. For every value of x is always alternating in sign, so we can just use the alternating series remainder estimate. So the error is at most the next term along. So here the next term was going to be negative x to the 7 over 7 factorial. The error is the absolute value of that, or the positive part of that. It's going to be the absolute value of x to the 7 over 7 factorial, or the absolute value of x to the 7 over 50, 40. And then we know that x is between negative 0.3 and 0.3. So that means absolute value of x is less than or equal to 0.3. So we bound this by 0.3 to the power of 7 over 50, 40. It's around 4.3 times 10 to the negative 8. So this is a really good approximation of sine x if x is between negative 0.3 and 0.3. Okay, so just to summarize, this section is about approximating functions by Taylor polynomials, or the first part of their Taylor series. If we do that, then we're going to be interested in how accurate is the approximation. To answer that question, we have to study the remainder. If the Taylor series is alternating, then we can very easily just look at the next term along. It's the alternating series remainder estimate. If the Taylor series is not necessarily alternating, then we have to go back and use Taylor's inequality. So we'll see some more examples of this in class. Thanks, everyone. See you next time.